Today we're going to be primarily concerned with one thing, tree height. So before we get to tackling it and making tree height better, let's understand what happens with binary search trees. As you guys know from the previous lecture, trees can range from bushy to spindly. And the difference between the two is actually really significant. How significant? Well, that's my first question of the day. So what I'd like you to do is think about the nice bushy tree we described versus a spindly tree, and tell me, in terms of n, the number of nodes, what is the height? Now I've given you an example here. This is a tree with 15 nodes and height 3, and another tree that has 4 nodes and is of also height 3. So try and answer this question in big theta notation, and then we will proceed. Okay, let's start with the spindly tree. For every item you add to the spindly tree, say it's length 9 or 10 or 11, its height will be n minus 1. So in that case, the height is just theta n. On the other side, the bushy tree, well, its height is going to be log n. Why is that? Well, let's suppose we wanted to go up to fill our next entire level. That is, we want to get a height 4 tree that's totally full. In that case, we would need to add 16 more items. For each of these, we need 2 children. So that, as it happens, is about double the existing tree. There are 15 items here. We need 16 at the next level. In order to get to the next level, we need 32, and so forth. And so what that means is, between each totally full, nice bushy tree, we have to actually double the size of the tree, and as it happens, that is exactly logarithmic performance, or logarithmic height growth. Okay? Now this is really important for real-world performance. A tree like this, the time to do a contains operation, because it's bushy, we can very rapidly get to any leaf. But with the spindly tree, it's actually just basically degenerated into a linked list, which isn't so great. Okay, so we'll get to tackling this problem in a moment. But first, I want to address a personal quest that I am on to instruct you about a thing I consider important that's a little obscure. So what I'd like you to do is tell me which of these 3 statements is true, just as a little bit of an asymptotics review. Hopefully you're pausing the video and thinking hard. So it turns out all 3 are true. How can that be? Well, as you guys know, a worst case tree has a height that grows exactly linearly. It's theta n. We already said that. Now, because the worst case is theta n, that means that all cases are at worst big O of n. So in other words, because the worst case has a height that grows exactly linearly, then every single BST out there has a height that grows linearly or better. Okay? So it'll be linearly if it's spindly, but if it's bushy, it'll be log n. Since log n is less than n, it's safe to say big O of n. Recalling that big O, you could think of it like less than, whereas theta, you could think of it informally as equals. Lastly, we have that BST height is big O of n squared. Now this one might seem puzzling at first, but it is, remember that big O means less than or equal. Like informally it means less than or equal. So we know that all BSTs have height that grows quadratically or better. Let's consider the worst case tree, the spindly tree. N, well n is less than or equal to n squared, so the statement is still true. Now this right here isn't as great of a statement. It would be better to say big O of n than big O of n squared, but it's still a correct statement to say big O of n squared. It's still accurate mathematically. Okay, so that's one issue I want to talk about. Next, which of these statements is more informative? Now I'm giving you 2 choices. So we basically ruled out and said big O of n squared, you can say that, but it's not necessarily a useful thing to say. So how about these other 2 choices? Since they're both true, which one do you think is more informative about binary search trees? Okay, so in this case, the correct answer is the top. It is more informative to saying that the order of growth in the worst case is theta n than to say that the height is always less than or equal to n. So let's see a little analogy to demonstrate why this is true. Let's suppose I have 2 statements about a hotel that could be true. The first statement is the most expensive room is $639 a night, and the second statement is every room in the hotel is less than or equal to $639 a night. Which one is more informative? Maybe a different way of thinking about it is, let's say I'll give you a free night at either hotel of type A or a hotel of type B. if you wanted to maximize your luxury, what would be the better choice to pick? All right, my shirt's red now, but it's not because I'm an evil version of myself. Don't worry. So A, it turns out, is the better answer. The most expensive room in the hotel is $630 a night is a more informative statement. Now, why is that? It seems like somehow they're kind of the same. Well, let's consider the Ritz-Carlton Lake Tahoe, which at the time I made the slide had a room that was $639 a night as its most expensive. It is also the case, if we look at statement B, that if we look at some place like the Comanche Motel in Fort Stockton, Texas, by the way, it's a great place to go. They have Merle Haggard karaoke. It's very cheap. And yeah, if you go, let me know. Anyway, this hotel, or motel really, every room in it is less than or equal to $639 a night. In fact, quite a lot less. So there's a giant class of hotels that all satisfy this condition B, whereas only a relatively small number that satisfy A. Now this seems a little silly, because if someone says, hey, every room in that hotel is less than $1,000 a night, you assume they're not trying to do some trick. But nonetheless, the statement, if we just look at the factual content contained in the English statement, it does not rule out, for example, the Comanche Motel. Okay? So this is basically just the same situation with big theta and big O. Binary search tree height, okay, so it's all four of these things. It is big O of n, because binary search tree never has height that is greater than n asymptotically. It is theta log n in the best case. It is theta n in the worst case. And we can also say, for example, that it's big O of n squared. And that would be kind of a jerk thing to do, but it is technically true. So these middle two statements, they are more informative. Big O is not mathematically the same thing as saying the worst case. For example, binary search tree heights, they are absolutely 100% big O of n squared. That is, they are less than or equal to the order of growth n squared. However, they are not equal to quadratic in the worst case. This is, you could think of it as an inequality. Now, all of that said, I'm being very pedantic, but I should acknowledge, and you should know, that in the real world, people often use big O as shorthand for worst case. Just like if somebody says, yes, every room in that hotel is less than $1,000 a night, like in your mind you think, okay, there's probably a room that's pretty close to that cost. Otherwise, why would you be telling me this weird fact? Okay? So just be aware that big O is often used in the real world as a shorthand for worst case. And you may wonder why we're going into all this pedantry, and it's because I think that if you're going to be among the best computer scientists in the world, you should get this little detail correct. Now, big O, it is absolutely a useful concept. Even though it is less mathematically precise than big theta, it is, as I've said, really convenient for being able to be less wordy. So instead of having to say something like binary search is theta log n in the worst case, you can just say binary search is big O of log n, and we're going to assume that when someone says something like that, they're not trying to trick us and pick some larger function here that is not a type bound. Now, there's other reasons that big O are useful, above and beyond linguistic convenience. So for example, sometimes we don't know the exact runtime, so we use big O to give an upper bound. As an example, if you wanted to write a program that can find the shortest route to all world cities, under certain assumptions I haven't listed here, the runtime to do that, all I can tell you is that it is big O of 2 to the n. There might be a faster way, but nobody knows one yet. Like maybe there's some better algorithm, but as far as we know, this is the best we have so far. So all I can say is it's big O of 2 to the n because there exists no good algorithm. And then lastly, sometimes it's easier to write proofs using big O than big theta. So for example, in the asymptotics 2 lecture, we took apart the merge sort algorithm and we assumed that our arrays were always a length that was a power of 2 for convenience. Now if I don't want to make that assumption, I can say, let's round up to the next power of 2 and then find a big O bound. That's a little beyond the scope of the class, but I just wanted to put it out there. And if you'd like, you can look at this in the A-level study guide problems for that lecture. Okay, so to wrap up, binary search tree height, it is theta log n in the best case, theta n in the worst case, and often folks will just say big O of n. So now, let's discuss the actual runtime and performance of our BST operations.